Hi, everyone. Hope you're doing well today. And for this last lecture of the week, we're gonna continue with the electric circuits. And because I know I'm gonna have the question anyway, I'm gonna address it so there will be a quiz on Tuesday next week, and it will be on mainly electric circuits and dielectrics, capacitors and dielectrics. But yeah, I would say on the capacitor dielectrics, probably more on a electric circuit point of view rather than on the focus of calculations of Gauss's law and stuff like that. So mainly electric circuits and capacitors. Okay. So yesterday, the main takeaway from yesterday were the two Kirchhoff rules we've seen that are very important, and combined with Ohm's law and a few reasoning on electrical circuits will help us solve any electrical circuits we're gonna encounter. So the first Kirchhoff rule pattern on the current and what's happening on the current when there's a junction. And basically, it says that the current is conserved at the junction, and so the current flowing in is equal to the current flowing out. And so if we have, for instance, three wires going out of the junction, then the sum of the currents on all three wires is equal to the inflow current. And yeah, yesterday during office hours, I had questions. So I want to clarify that the current that's going to be in each of those lane of the junction will depend on what's next on, for instance, the resistors and stuff. So it's not just evenly reparted at the junction. It really depends on what is after. And basically, for instance, if you have a very massive resistance on one of those, the resistance will almost not let any current flow. And so in that situation, the current will be very low on that part of the junction. And conversely, if you have a very small resistance in the lane, then most of the current will go through that. So yeah, be careful. It's not just evenly distributed. It depends on what's after the junction. And the second Kirchhoff rule is pertaining the voltage, the potential in a closed loop. And it's also named the loop rule. And basically it says that the sum of all voltages in a loop is equal to 0. And then you have to orient them depending on the orientation of the potential. So basically for a battery, if the potential is given positive, then the other one are opposed because the potential drops, and while the potential increases for the battery. You might sometimes encounter a battery that would be reversed. So sometimes the potential could be given negative. So that just means that the plus and minus direction could be reversed. So just be careful about the direction of that. So yeah, basically the loop rule say that you have potential start from the maximum potential given by the battery and then loops back to 0. And in any loop, even if there's no battery, it means that the sum of all potential will be 0 if you orient them correctly. So let's look at an example to apply those principles. So first, let's try to find the total current flowing out of the battery. So we have a battery, and then it's connected to two resistors that are in parallel. And then let's see which bulb is brighter. So to get the total current, what we can say is that this circuit is equivalent to circuit with a single resistor. That would be the equivalent resistance given by the combination of those two resistors in parallel. And then we know that to obtain the equivalent resistance of parallel, we just add, we add the inverse of the resistance. So we have 1 over R1 plus 1 over R2. And if you put those two at the same denominator, you get 1 over R equivalent is R1 plus R2 over R1, R2. And so if you take the inverse to get the actual resistance, then you get this value for the equivalent resistance. And so using the values, give us a resistance of 8.3 ohms. And you see that 8.3 ohms is lower than both of the resistance, and especially is lower than the lowest resistance. So this is something we've seen, is that if you have resistors in parallel, the equivalent resistance is lower than the sum of all resistance. And it's pretty intuitive to understand why, because it means that for the current that's coming here, if it had only this resistance here, then you can only go through that. But now you can go through this path and this path at the same time. So having two resistors in parallel and if you think about the resistor, it could be seen as a wire of some resistance. And so if you're adding another wire in parallel, that has some resistance, or let's say a tube then you see that what you're doing is that you're increasing the area of your material. And we've seen that the resistance of a material was proportional to its length, but inversely proportional to its area. And so if we have two resistors, we see that we have more cross-section. And so we're increasing the conductivity, and so we're decreasing the resistivity. So that's why having two resistors in parallel decreases the overall resistance, because basically it gives more path for your current to flow. Okay. And then when I retrieve the total current, so then it just using Ohm's law, it's the potential it's the potential V at the edges of the equivalent resistance, and we see they just connected to the battery, and so they are equal, and it gives you that V is the battery potential divided by the equivalent resistors to get the overall current. And so if we do that, so it's a 9-volt battery, we have a 8.3 equivalent resistor, and so that gives us a current of 1.1 amps. Okay. So now let's look at which bulb is brighter, or which resistor is dissipating more energy. So since they're in parallel, we know that they have the same potential. Yeah, let's have another look at the circuit. So we know that P is equal to U multiplied by I, or V multiplied by I. It's also equal to V square divided by R. It's equal to I square multiplied by R. So, here we could use both this one. This one, we have both the potential and the current now, so we can just assume, use this one. but it's also useful to no, scratch that. No, to use the current to know the power dissipated in those resistors. And we know we just got the total current here, but there's a junction here, and nothing tells us right away what is going to be the current in either of those two. We know that the sum of those two is equal to the total current, but then to get the actual current, I1 and I2, we would have to use the just Ohm's law on each of those. So we could do that, but we know that those two are connected to the battery, and they are seeing the same potential difference V. Here we have the same potential, and it's V because they're connected to the same ends that are connected to the battery. And so we can just use this one because we know the potential and we know the resistance of each. So in that case, this one makes more sense to use right away. And so if we do that, then for 10 ohms resistor, we calculate V squared divided by the resistance, and it gives us 8.1 watts. And for the other resistors, now we have 9 volts square divided by 50 ohms, and that gives us 1.6 watts. See, it's 5 times smaller. And that's coherent with what we've seen before for light bulbs, where we said that's when they were connected in parallel. The one that has a smaller resistance is the one that dissipates the most power because it has more current flowing through it. Okay, let's have a look at this situation. We have 4 identical light bulbs or resistors, and they're organized in that order. And here we have an open switch, electrical switch. And so when it's open, the current is just flowing like that, and kind of forgetting about this. But then we're closing that, and then we have those two loops. So what's happening? The brightness of bulb A, B, and C when we close the circuit. All right. So the correct answer is number 4. Let's see why. So if we close the switch here, what's happening is that now we have a situation where we have B and C that are in parallel with this new resistor. And we've seen that the equivalent resistance of resistor in parallel is smaller than the smallest of all resistance. So that means that now the current flowing through the overall circuit is larger. And one reason, I mean, one other way to think about it is now we have an additional path for the current to flow through. And so there's more avenue for current to flow. And so we're increasing the current going overall in the circuit. And so here, since all the current going passing through the circuit pass by A gets brighter. But the thing is, since the resistance of A hasn't changed and we increase the current, then the potential drop from the edges of this will be larger. This potential here, U or V, this potential here, V, is equal to the resistor multiplied by the current. And we've seen that we're increasing the current passing through. And so this potential has to be equal to be larger. And the potential, applying the loop rule, the potential in this overall loop here of A, B, C, and connected to the battery has to be 0. And the potential of the battery hasn't changed. And so the potential at the edges of B and C has to be smaller. And so if the potential is smaller here, then there's less current flowing through them. So we have a drop in current through those, and so therefore less power dissipated in B and C, so they're dim. Does that make sense? Okay, new situation. So we have a battery here, 3 resistors, and these resistance in the home, right? So for which resistor the current is the largest? Right. So the thing to remark here and to just notice is those resistors here are just in parallel. There's just one loop. There's just one loop, and the beginning and end of each resistor are, the end of this resistor is connected to the beginning of this one, and so on. And so there's only one loop. There's no junction here, and so the current has to be conserved everywhere. And so the current is the same everywhere. And yeah, and if you wanted to get the equivalent resistance of everything, since they're in series, you just add them and you would get 560 ohms, adding all these 3 resistance in series. So be careful for those who answered number 1. I don't know if you forgot that the current is conserved in a loop. I mean, the current is conserved in a closed circuit with no junction of this corner organization here made you think it was not in series, but be careful about that. Okay. So we've seen a few examples now, and we've seen resistors in series, resistor in parallel, but we're gonna continue advancing and think about what's happening. How can we solve situation where we have more complex circuits, where, for instance, we have resistors like that are in series, but also in parallel. And so it's not so straightforward to get the answer. And then, so yeah, let's see how we would get the total current going through here, but also the uh, the the current going through each of those resistors, and then the power dissipated in those resistors. So the first thing is to take things sequentially. And so first we see that we have those two resistors that are in parallel, so we can combine them together and find the equivalent resistor. And then we'd have, just an equivalent resistance that would be directly in series with that one. And so we can combine them using the series rule. And then we have just the overall equivalent resistor. And so we can get the full current. And then knowing the current here, we can use first Kirchhoff's law to know that these two currents here are going to be equal. The sum of these two currents is going to be equal to those. And so we can we sum equal to those. And then we also know that the potential across this whole loop here is going to be 0. So 12 plus, minus this potential minus this potential, it's going to be equal to 0. And so using all of these laws, we can retrace each current and its potential and get a total characterization of the circuits. It's not very complicated, but it's tedious, and you need to apply a thorough sequence to do things cleanly. So how to do that? First, if you have a messy circuit, sometimes can be made intentionally or not, but sometimes circuits can be drawn in a slightly unclear manner where you don't see clearly series and parallel connection. And so if that's the case, you should redraw it so it's very clear which one are in series, which one in parallel, so your mind clear. Then you should find equivalence resistance of circuits and do that sequentially, taking all resistance that are in series and in parallel, one with each other, and find equivalent resistor up to the point where you have only one single resistor. That would be the total resistance equivalent, the total equivalent resistor. Once you do that, you can get the total current using Ohm's law, using this equivalent resistance. And then you can find the voltage drop across resistors that are in series using the fact that the sum, the equivalent resistance of those. And then you can use the loop rule to find voltage drop across remaining resistors. And so once you have the voltage drop across all the components, we can access the currents using Ohm's law, and therefore finally get the power through each resistors. So all of these steps are pretty simple. It's just some logics and then some easy calculations to do. But you see that you can, there's a lot of steps, and you have to have a nice and clear procedure to be able to do that in the right order. So let's apply this method to our circuit. So it's just showing you back the initial circuit. So what we do is first we get the equivalent resistance of this parallel connection here. So that gives us the equivalent resistors that we call R23. And then we have those two resistors, so R1 and R23, that are just in series. So it's pretty straightforward to combine them. So R23 using the this formula we've seen for parallel resistors is going to give us 210 ohms. And then R123, which is the equivalent resistance for all of these resistors, is just the sum of R1 and R23. And so that gives us 90 ohm plus 210 ohms, so 300 ohms. So this is the R total. And so then we can get the total current going through the circuit just using Ohm's law through these equivalent resistors. So we have the potential, it's the potential given by the battery, and we have the equivalent resistor. So using Ohm's law, we see that the current is going to be 0.04 amps or 4 milliamps. So go back to the circuit. Now we have this current. So in our procedure now, to get the power dissipated in either one of those resistors, we are going to need the potential drop across those resistors. Using that potential drop, we will be able to retrieve the current that flows through them, and therefore, or instead, even without doing that, if we have the potential drop, we can just get the power dissipated using V squared divided by the resistor. So we're looking to get V2, the potential across those two resistors, and it's the same because they're connected in parallel. So first, we want to get the potential drop across the first resistor, because then we can apply the loop rule in the overall large loop. So this voltage drop across these resistors can just be obtained using Ohm's law, because we have this total current and we know the resistance value. And so we see that the potential drop here is 3.6 volts using Ohm's law. And then we can apply the second Kirchhoff rule to the overall circuit. So I'm gonna just draw it quickly. We have the first resistor, then separate into and then reconnect, and then you close down. And so here we have 12 volts. Here we just we just calculated that this is 3.6 volts. And using the loop rule, we know that if we do this loop here, then we're looking for this, let's call it V2. It's also V3, right? It's the same potential. So we're looking for V2, and using the second Kirchhoff rule or the loop rule, we know that the total potential across the loop is 0. So we have the battery potential minus the potential drop 3.6 minus the potential we're looking for by V2 that is equal to 0. And so just moving this to the other side, we just have that V2 is 12 minus 3.6. And so it's 8.4 volts. And because they're in series, in parallel, my bad, we know that V2 is equal to V3. V2, we have V3 here, and they're the same. Okay, so we are almost done, because we still need to get, now that we have the potential drop, we can get the power dissipated using V square over R, but we want to be done and completely characterize the circuit. So let's get also the current flowing through those two lane of the junction. So using Ohm's law, now in this V2 here, in this second resistor, we just have the current through this resistor is going to be the potential drop divided by the resistance. And we know this, it's a given of the problem. And we know the potential drop because we just calculated that. And so we get that the total current is 0.03 amps. And so we have the current here. That's 2. Okay. And now what about I3? So I3 now, we've done all the work. So no I3, we can do just the same thing. We have the potential drop, and so it's 8.4 volt divided by the resistance, which is 700 ohms, and so that gives us 0.01. But to be versatile and not using always the same trick, we could also have used the first Kirchhoff rule, saying that here we have a junction. So that means that I is going to be equal, the total current is going to be equal to I2 plus I3. And we just got I2, which was 0.03. We calculated at the beginning that this was 0.04. This was 0.04. This was 0.03. And so naturally, we get that I3 is just 0.01. And so those two give the same thing. And that's a good check that we did the right thing, because those two methods should give the same result. So we got the same thing, so we're happy about that. Yeah, and then for the power dissipated in the R2, so now we have the current and the potential, so we can just multiply those, or we could have directly used resistor square divided by the resistance, potential square divided by the resistance. These two are going to be the same anyway, but here it's your choice what you want to do, as long as you have the right value, give the same power in the end. And so here we get that the dissipated power is quarter watt. Okay, so is that clear? Is there anything you want to go over again? Because this is going to be kind of a textbook example of what to do in your situation. It's probably going to be one of the simplest complex circuit you can encounter. There's just 3 resistors, one with 2 in parallel, and that's in series with the other one. But it's it has everything you need to do. Apply loop, and apply both Kirchhoff rules and Ohm's law. If you do right in the right order, then you get sequentially to the right answer. So this is an example I strongly encourage you to go over again. Maybe do a small, do a small variation at home, or just try to retrieve that with different values and see if you can get to the correct answer. But yeah, this is a just a nice simple example that has everything into it. So we have those four identical light bulbs connected to this battery in a relatively complex manner. Which bulb will be the brightest in that case? All right. Yeah. So you've guessed it, it's this one here, the bulb number A. And the reason for that is, once again, current is conserved uh, overall. So here we have the total current going through the circuit. And then here we have a junction. So we have that, let's call it that I1 and I2. So we have that I is equal to I1 plus I2. So we see that the current going through A is larger than any of those two current because some of the current is going through this, some of the current is going that way. And so obviously there's less current in each of those two parts of the circuit. So the brightest bulb will be the first one. Oh, yeah, because they are identical. But I'm thinking, wait, it might be also the case for any. I would have to think about this for a bit, but I think I square. No, maybe not. Yeah, it might be a situation where, yeah, no, that's not right. Yeah, but if there's identical, then yeah, power. Yeah, it has to be identical for this to be true all the time. So okay, similar situation. These bulbs are still identical, and now we know that the EMF of the battery is given as this is E. So what's the total current flowing through that battery? So basically, what's this I? Okay. Um, okay, I gave you some time to think about that. Seems like most of you have the right ID. It's uh, number four. So for once, this is a quiz and needed some to think to calculate a little bit. So basically, to get to that point, you just need to get the equivalent resistance of the circuit. And so first we have those two in parallel, so C and D. And so we know that the equivalent of those two, let's say they're equivalent. So let's say the resistance of one bulb is R. Yeah, that's given here. So this equivalent resistance of those two in series is 2R, and this is 1R. And so they're in parallel, and so the sum, I mean the 1 over the equivalent of all of this is 1 over R plus 1 over 2R. That gives you R equivalent equal to 2/3 of the initial resistance of one bulb. And then this one is in parallel with this equivalent resistance we just got, and so we just add the value. So we have 2/3 plus 1, which is 3/3, and so we have wait, three-third. Yeah, 3/3, and then we have this, which is 1. So that's 5/3. Oh. Hmm. Yes. Oh, I see. Yeah, I have. Yeah, so yeah, shuffle. I guess my answer is shuffled in the wrong uh thing. So this is the right answer, 5/3. So that's what I was getting to. And yeah, so the correct answer is number 2, and this is correct. So yeah, well, that's why I was getting confused. I guess I shuffled wrongly my answers. So I guess most of you guessed wrong, but maybe because you had you're looking at the slides uh, I put online with the that had the answer. But yeah, okay, I'll try to think about modifying this. But yeah, so okay. So this, what we've done until now, worked when we can, directly simplify our circuits to series or parallel combination of resistors. But we can imagine situation. Is that not? Uh, yes. Oh, I see. Yeah, the question was asking for the current. So EI is equal to E divided by R. Yeah. Okay. Yeah, my bad. Yeah. I was getting the yeah, that's indeed. I was getting the resistance and I get confused, but you're right. Uh, it was correct because yeah, current is expressed as the voltage divided by the resistance, and so since the resistance is equal to 5/3 of the initial resistance, then when we take the inverse of that, we get 3/5 uh, 3 divided by 5 IR of the EMF. So yes, thank you. Sorry about this little confusion. Okay, so yeah, what I was saying is that sometime you can get a circuit that you cannot just uh, simplify to be a simple combination of series and parallel resistors. For instance, here we have this kind of complex arrangement of resistors, and we see that here, these resistors are neither completely in series or in parallel. They're creating loops, but this point here, I mean, these two resistors are not in series, but they're not in parallel because they're not connected to the same point. So when this is happening, we cannot just simplify everything and get the equivalent resistors. And so in that case, we are into a slightly more complex situation. And we have to rely only on a combination of the Kirchhoff laws, so the loop rule and the junction rule, to get the overall current. And so what we are going to do is use the loop rule in different loops in the system to get to have access to all the currents. So here, for instance, we see that. So if the resistor, are characteristic of the problem, we're not trying to guess resistance; it's given by the problem, as well as the potential given by the battery. So here we have the current here. And we know that this current is going to be equal, I is going to be equal to I1 plus I2. And we know that here we can call this current I3. And using Kirchhoff's law here to this new junction, we know that I2, I mean, this new current here is going to be equal to I2 plus I3. And here, if we use Kirchhoff's law here, we see that I1 going to be equal to I3 plus this current here. And so this current is equal to I1 minus I3. Let's call that I4. And so I4 is just equal to I1 minus I3. So we see that here we can basically express everything as a function of those three current I3, I1, I2, and I3. And so we basically have a problem that has three unknowns. And so we'll need three equations, three loops to get access to these three unknowns. And we need to have all three of those currents in our loops. So for instance, we can use this loop here, loop number 1, and say that the potential all across this loop here is going to be equal to 0 according to this second Kirchhoff rule. So this gives us the potential drop. I mean, we have the potential drop here, and that gives us a relation about with this potential drop in the first resistor and the potential dropper in this resistor. Now, if we take the second loop here, we have the same thing, but with the outer resistor here. And now we can use also the inner loop here, and we can apply the potential loop, the loop rule also to that closed loop, because it's a closed loop. Even though there's no battery, you can apply this. Just have to be careful about the direction of the current and know which one to subtract and add. So let's see how it works out. So in the first loop, as I was saying, we have the potential here, 13 volt. Then we have the potential drop across this resistor. So it's the current across it multiplied by its resistance, 1 ohm. And then we have that the potential drop across this resistor is the current that flows through it. So it's I1 minus I3 multiplied by its resistance. And it's, again, 1 ohm. And so using the loop rule, we know that this is equal to 0. If we do the same thing in the loop number 2, then we have 13 volt minus I2 here multiplied by the resistance of this resistor, and minus the current here through multiplied by this resistor. It's going to be equal to 0 because we have a closed loop between all of these points. And then if we take this loop here, which is different from what we've seen before because there's no potential here. And so we see that in that case here, we have that I1 minus I1 multiplied by the resistance minus I3 multiplied by this resistance. And here we have to be careful because to close our loop, we have to go against the current here. And so it's here we have to use the plus sign here because it's going against the flow of current. And so here we have to use a plus sign, and that gives us the potential drop all across this loop here. Okay. And so we have these equation that relates I1, I2, and I3. And we can also use this Kirchhoff law here. So gives us the relation between I2 and I1 and I3. So I2 equal I1 plus I3. No. Let's backtrack. So we have these three equations, and we have three equations, three unknown, and so we should be able to retrieve each of those unknown. Okay. And so let's start with that one here, where we have I1, I2, and I3. So we can express using the third equation, I2 as a function of I1 and I3. And then we have this relation for I2, and so we can inject it into the second equation. So we replace I2 by its value of I1 plus I3 in every steps. And then, so we have an expression that gives us a relation between, we simplify and we just have an expression that gives us I1 and I3 together. And then if we look at the first equation here, we have expressed I1, and we have only I1 and I3, and so we can express I1 and I3. Now we have this expression between I1 and I3, and so we can get rid of I3 here. From this equation here, if we add 5 times this first equation between I3, we're gonna get rid of this I3, and then we have 10 times I1 that is added to this, and 5 multiplied by 13 volts that's also added to this equation. And so that leaves us with 78 volt is equal to I1 multiplied by 13 volts. So now we have an expression, for I1. I1 is well defined. And so we can replace I1 in the first equation here, and then we find an expression for I3, which is minus 1 amps. And we get I3, and it looks like it's negative. That's weird, but actually, if we come back to this circuit, we oriented I1, I3 in that direction, but it was because we needed to orient it one way. But it just seems like we picked the wrong direction, but that's all right. Just we oriented that way and we obtain a negative current. And so it means that it just oriented in the other direction. And that's fine. If we just orient it that way with negative current, that's the same thing. So when you don't know, we have this kind of junction and you don't know where the current is going in which direction, then you just pick one and then you do your loop rule accordingly, and then you'll end up with the correct result. And it might be that you chose the wrong direction, and that's fine. You just get a negative number for the current, and you can you actually know where the current is flowing. Okay, and so after this step, we have measured I1, measured I3, and now we can use the third equation that was giving us I2 as a function of I1 and I3. And so now we can use that to get I2, and we get 5 amps. And so doing that, we have I1, I2, and I3, and this is expressed as a function of I1 and I2, so we have it too. This is I1 minus I3, so we have expressed it, and this one is I2 plus I3. And so we have expressed it too. So we just needed these three currents to characterize the whole system. And then if we wanted to, we can get the power dissipated in each of those because we have the currents. And yeah, that's it. Our system is fully characterized. So yeah, I understand this is not the easiest to follow because it's solving system of equations. It's kind of a tedious work, and sometimes you just have to pick. You can mix equations as it seems the more natural to you. So again, that's something if you want to really get a good grasp of it, I really encourage you to do it at home. Start from the first diagram, apply the voltage loop rule, and try to get to the same result. And it doesn't matter if you use exact same steps as I did. You can use different steps as long as you it will go as you expressed one current as a function of the other, or one current as a function of two others, and then you substitute that into another one of the equations, and then you should have the expression of one current as a function of only one another, which now you can substitute into the other equation. And finally, you get the first current. And so with that, you can get the second current. And with that second current, you can get the third current. And so you need as many loops as you have unknown current, and you have to be careful about just having enough, using enough current, as much current as you need, but not too much. Like here, 3 are enough to characterize everything. So if you were to add another 1I4, then you'd use 4 equations, and then see that some are redundant, but we would have to done more work. So be careful about your analysis of the current you actually need to fully characterize the system. And then just a sequential characterization and solving of your linear equations. Okay. So there's another method it's basically the same method, but we'll see that we can solve those circuits with using linear algebra. So for instance, if we have this system, so we have two batteries here at both ends, and then resistors oriented that way. So we see that now it's a little bit complicated, and we cannot add those in parallel because there's a resistance between them, so they're not in parallel, and they're neither in series because there's always a resistance between them. So it's a complex situation, and we have to use the loop rule to solve that. So what we would do, we do the same thing as we just did. We apply loop rules in in those 3 loops. And so if we apply it in this inner loop here, we have V1, or I guess in that case, it's reversed, but just a minus sign. So we have minus V1 plus the potential in here plus the potential across here. So here we have I1. And so the current going through that resistor is going to be, this is I2, this is I3. And so the current going through that part is just I1 minus I2. That's just the part of the current that, it's Kirchhoff law using this separation. And so we have this expression here, and we can rewrite it that way, factorizing for I1 and I2. We do the same thing in the second loop here. We have that, we have the same current here, I2 minus I1 through this resistor, plus I2 multiplied by R3, so the current, the potential across this one, plus the potential across that one, I2 minus R3. This is I2 minus I3 in that one. That goes through this resistor. So that gives us a second equation. And then we can do the same in the third loop. So this time we also have an EMF source here. So we have to take that into account. And so if we do that, we obtain the third equation linking I3 and I2 here. And the potential V2 that's given by the problem. And so we have three equations, three unknown, and so we have a linear system we can solve. And you might have seen in math, when doing algebra, then you can solve a linear problem using matrices. And so you can write it that way. So, you have R1 plus R2 multiplied by I1 minus R2 multiplied by I2. And multiplied by 0 plus 0 multiplied by I3, because it's not in the first equation. I3 is not in the first equation. So just rewriting this equation here in matrix form. So see, R1 plus R2 multiplied by I1 minus R2 multiplied by I2 is equal to the potential. And so we're just writing that in matrix form. R1 plus R2 minus multiplied by I1 minus R2 multiplied by I2. And I3 is not there, so it's 0. And then that's equal to V1. Do the same thing for the second equation. So minus R2 multiplied by I1, the sum of all these three resistors multiplied by I2, minus R3 multiplied by R4 multiplied by I3 is equal to minus this potential. And same thing for the third equation, we write this way. And so we have, written this linear system in a matrix form. And that might seem like a complication at first because, just had a system and now we have a matrices that come making things more complex. If you remember your algebra courses, then you have basically, let's say we give those resistor value of 1 ohm and V1 and V1 5 volts and V2 minus 6 volt. Then our system becomes this, and we want to solve to get access I1, I2, and I3. And so we have basically initially this system here that represents our system of equation. So this is R, this is the matrix current, and this is the potential current. And you see, it's interesting because this matrix algebra equation is, we retrieve the Ohm's law, but in a matrix form. Here we have the resistance matrix, the current matrix, and the potential matrix. And we see that they follow Ohm's law. And so using Ohm's law, we can write that the current matrix is equal to the inverse of the resistance matrix multiplied by the potential matrix. And so we see that if we just calculate the inverse matrix of this resistance matrix, we just have to multiply this inverse matrix to the potential matrix, and we get the solution of our system. And yeah, so you could just use what you know about inversing matrix to do it manually, but you can also input this matrix in your calculator or in a software like MATLAB or Python, and then you would get the solution. You get the solution for this inverse matrix, and then you could multiply it to this potential matrix and get the result. Okay, so yeah, I mean, I feel like this is mostly for your own knowledge. Probably won't be asking you to solve it that way because it's pretty new and we won't have time to really practice that way. But I mean, once you're more familiar with algebra and you have the nice method, you see that it's a really easy way to solve this kind of problem. So if you want to do it that way, that's fine. But otherwise, the good old, substitution method for linear equations is totally valid and probably the safest way to go for those kind of problems right now. And but the thing about matrices is that when you get really complex systems, I don't know, let's say you get 10 currents or 10 unknown current, then you would have to solve like 10 a system of 10 equations by substitution, and that's way too long to do manually. So the matrix system comes handy in that case. Okay, guess it's almost the end. Just wanna add before we end for today, wanna go over a few last things. So something we haven't mentioned yet, but if you add batteries in series, you just add the voltage together. So if you put, for instance, two batteries, minus plus in series, and these batteries are 1.5 volts, then you end up with just one 3-volt equivalent battery. And okay, and is there something else I wanted to do? Okay, and this we'll do Monday before getting to the rest. Okay, so do you have any questions on what we did today? Or otherwise, I wish you a nice weekend. Get started with your, with working get prepared to the final next week. So you can start reviewing some stuff we did earlier. Remember, you have also homeworks on mastering physics to do. So don't forget to get going on those if you're a bit late on that, because you have to get them done for the final. So don't get caught up in all of that.